deadlock and starvation.
Deadlock happens to more than one process, whereas starvation happens to only one.
Yep, a deadlock can only happen to more than one process, two processes or more, while starvation may happen to a single process. Anything else? Is it possible for processes, deadlocked processes to come out of a deadlock? Not without an outside intervention, no. While a starved process may get what it needs and might come out of starvation, but it might go indefinitely. How do we get rid of a deadlock if a deadlock happens? What's the best way to overcome the deadlock? Say again?
Remove one of the deadlock processes.
Terminate one of the processes, or terminate them all, or terminate the deadlocked processes, but obviously the better one is to terminate one of those processes. Which process would you recommend to terminate in a group of deadlocked processes in order to... Are you finished?
That works for...
No, I have somebody else. Right? Yeah?
Let's start by seeing what ones aren't written to databases and ignore those.
Eliminate reading processes rather than writing processes to databases. Yeah? Any other suggestions?
You might choose to eliminate a process that is holding on to a lot of resources.
Yeah. Select the process that has a lot of resources held, so hopefully that'll give a better opportunity of eliminating the deadlock. Any other recommendations?
That has less CPU time, like less done.
Process that has done less CPU processing, right? You'd eliminate rather than the one that's been running for a long time. Yes?
Yeah, because if you eliminate the one that's run for a long time, it'll have to start up again.
Yeah, so don't pick the process that has been running for a long time. Yeah. Pick the one that just started. I think so. I wasn't too sure. Right. Any other factors were indicating which process you might select? Yeah, that's exactly the first one that was mentioned. The reading rather than the writing processes, or maybe processes which have a log of what they do, or they can step back and maybe not have to restart from the beginning the next time they need to run. Okay, how do we avoid deadlocks? What's the best way to avoid deadlocks? Any methods known for avoiding Banker's algorithm? And how do we prevent a deadlock? Eliminate one of those four conditions. Make sure one of those conditions is not in the system. Thank you. Everybody sign the attendance sheet? Good. Okay, maybe not. You did not fill out there. Was that intentional? Okay. How does a deadlock happen? Come on, guys, hurry up, come on. Thank you. Enough talking, guys. Talk to me. Tell me, how would you define a deadlock? What's a deadlock? Yeah?
One source request and resource at the same time. It is used to another source. And because the source is seeking an resource, it is called by this process and it's not a deadlock.
Yeah? Anybody can give me another description of a deadlock? What a deadlock is? Yeah, okay. So, an entanglement of resources and processes that ends up in a circular weight. What is mutual exclusion condition? What's that condition? Explain that condition required for a deadlock. It's called mutual exclusion. So a resource is a mutually exclusive if it can only be used by one process at any given time. It cannot be shared simultaneously. Right, what are the other conditions? Name another condition in deadlock that required for a deadlock.
Circular weight.
Circular weight. Non-preemption or non-preemptiveness. What's a non-preemptive condition?
Non-preemptive condition is when interruption is occurred by output.
Non-preemptiveness is what?
When no interruption is occurred to the process.
Okay, when a process cannot be interrupted. Can you add to that? What's non-preemptive in the deadlock conditions? Where a process cannot be interrupted and its resource taken away. So non-preemptiveness is taking away a resource from a process before it finishes with it or before it voluntarily gives it up. What's the last condition? Hold and wait. Is that it? What do we mean by hold and wait condition as far as the deadlock is concerned? Yeah, so if a process is allowed to hold on to a resource while waiting on another resource that's not available, that's called hold and wait. Okay, so we talked about multi-programming so far, where one single CPU can be used to execute a number of programs or processes, and the CPU is shared between them. So what multi or parallel processing that we're about to talk about is where we have a number of CPUs that can execute a number of programs, or a single program in that case. So we can maybe split a program. We have a couple of CPUs that are executing. We have one process or one job that we can split it into two parts and allocate each part to each CPU. That's one way of maybe utilizing multiple processes. Or just have more programs, but allocate one CPU to one program, allocates a separate CPU to another program. Depends on how we have those CPUs built or attached together. And the rest of the hardware that supports them. Memory, you could have maybe a CPU, you have memory, and the input-output devices that can be independent from another CPU, even though they're built into the same system. So each CPU can have its own memory and its own I/O devices, and all contained within one system, but they are kind of not strongly connected together. They're loosely connected together. But we can allocate one program to be executed by this CPU, another program by this CPU. But we can go into as far as splitting a program between the two CPUs and get each CPU execute some part of a program. In fact, you can depending on how the CPUs are connected, there are many ways to connect them, but you could get as far as maybe splitting one single instruction into different parts and pass each part to a different CPU. So you can hopefully get better performance, and you get all the CPUs working together, executing either the same program or multiple programs in order to get better performance. But we know from what we've talked about in the past is that if we have one CPU, multiple programs executing, and all competing for the same resources, and if these resources are not shareable, then we could end up having problems like the race problem or the deadlock problems. Once we start doing parallel processing, where we can have multiple processes executing on a number of CPUs, then we also can assume that they will, in many other implementations, is that they have all access to the same memory. So all CPUs have access to the same pool of memories and same pool of IOs. So they can all exchange data or pass data to one another or access the same variables, maybe queues and other data structures or stacks. And that's fine. It's great for cooperation between different processes, but it also comes up with its own issues and problems. So as well as deadlocks, as well as race problems, we can start having other synchronization problems between processes. And that's what we'll talk about today, is how to actually improve the synchronization. We'll look at some of the problems and some of the solutions to those problems. And one of the problems that we'll end up having here is that if you write program code, and if multiple copies of this code are executed, or maybe even different parts or different processes are running, they could be, most of the program can be executed while another copy of it, or different program or process, is being executed simultaneously at the same time. Normally, most of the time, there's no issue. But there are some instructions that if they get executed, multiple copies of them get executed at the same time, then we could have a problem. They came to be known critical code. So every program, they might have some parts of it are so critical that when they're executed, they should not be executed while another group of them or another part of it is being executed simultaneously. So maybe it could be accessing records, writing to a record, may not. So if the same program is accessing, or maybe accessing a queue simultaneously at the same time, that they should be controlled. Or if they are writing to a record, to a field, that they should write at the same, they should not be writing at the same time. Or just as with the race problem, that can happen if there is a variable here, and this variable, let's say, has the value 10, and we want to add, this process says, add 5 to this variable x, and this one is executed at the same time, says, add 5 to this variable. Normally, to add 5 to a variable, you need to upload first the value in that variable. So if you ask, if this is being executed at the same time, this instruction says, get me the value of this value of the variable x. So it says it's 10. This one says, get me that value in variable x, and it's 10. This one says, add 5 to it, it becomes 15. This one says, add 5 to it, it becomes 15. And this one says, write the new value to x, so it writes 15. But this one says, write the new value to x, and it becomes 15, when it should be 20 at this stage. So it was 10, we added 5 to it. Each process has added the value 5. It should end up with the value 20. So it did not. So that's the race problem. who or which process is the last one to write. The value will be based on the last process to write that value. But it's incorrect value. So if these processes are in parallel, working simultaneously, we need to control, or some parts of the code needs to be controlled, and now it needs to be controlled not by the operating system, by the programmer. So you need to be able to isolate, identify the critical code, and this is what we call the critical region of a code, of a program, and we need to control it. We say that's fine to execute those two processes simultaneously, but if you ever get into this code, this is quite critical, that make sure only one of the processes is running at any given moment of time. And when it finishes, give the other one to run. And to control that, we use the lock. We talked about the lock mechanism in the past, where we say, right, lock this process. If this critical region is being used, well then another process cannot start it. Hold on here, lock it up until this one finishes, and then let it go again. We've done something similar before on the resources. So if we were using, say, a file record that these two processes want to write to it, we used to lock that record while this one finishes reading or writing, and then allow the next process to do it. So there's a lock mechanism used. So we'll look at those mechanisms in order to solve the critical region problems and issues. So the first method we'll look at was used in the old days in the railway tracks, on the railway systems, and it's known as the test and set method. So we look at three techniques. First one is known as the test and set. And the test and set was used in the old trains as, just imagine that there is a train track running in a certain path, and train comes in, zooming through, happily going over. Now, as the train network expanded, they started obviously sharing some of the tracks. So the same track can be used by different trains. So we have a train going in this direction and a train going in that direction. Hopefully, this part here where they meet, they share it, but obviously it cannot be simultaneously used. So if this train sees that train coming, it has to wait until this train clears this area, and then this one can go in its way. Occasionally, they start having accidents. They're meeting in the middle. So somebody came up with this intelligent idea in the train systems where the handle actually moves up and down to let a train know whether the track is free or not. And the idea is simple. They had a sign that says the train is free, or this track is free, or it's being used. It used to be a handle that comes up or down, but we just refer to it as either the word free, the track is free, or it's busy. And we use 0 or 1 in computing just to indicate whether it's free or busy. So the train driver comes up from there, keeps an eye on that sign. Sign is big. On a distance, he can see that it's free. So what he does, he should book it and say, right, I'm going to be using it now. So the train has a lever here, so the train hits it and turns this free into busy. So if another train comes in, they could see the sign, oh, it's busy, I better stop and wait. So they hold on here until this train passes through. As it comes through here, it hits another lever here that turns this into a free sign again. Now this guy sees that, so he hits the lever to say, all right, I'm going to take it. It's busy now, so it goes in. So if another train comes while this one is crossing over the critical section, this is the critical section of the track, then another one will come in, but they see the busy sign, so they wait until this train goes through and turns it into free again. And now each train coming in, they first check the sign, they test it, they see whether it's free or busy. If it's free, they turn it on, to indicate it is busy, and they go through. So that's a very simple and straightforward sign, and it's worked for a number of years. And then every now and again there was another crash, and they couldn't understand why. And the reason they realized later on is that two trains were coming at the same time, one from this end, one from that end. The trains can't see one another. There's a big barrier between them. But they could both see the sign, and the sign says it's free, the track's free. So at the same time, each train driver will say, right, the track's free, I'll go. They'll hit the lever. They both do it at the same time. Suddenly this thing goes busy, and they think they're after booking that track for themselves, and they both start moving, and suddenly, oh, they crash. So the problem is that they do check simultaneously at the same time, and at the same time they think the track is free, they believe it's free because it was, and when they turn it on and they book it, they do it at the same time. So there are two problems. Well, there are many problems here. First, there's a time between the checking of the signal and the actual turning of that signal on or booking it. So those two, because you check first and then you decide, and then you go. So while this guy has looked and got the signal is free, he's processing it in his head, this guy has also looked. And then by the time this guy decides, yeah, I'm going to book it, this guy has already decided as well. So in computing, in programming, this is fairly simple. What we do is we use a variable, a small variable. Let's say we call it t or whatever you want to call it. And it has the value 0 for free or 1 for busy. So whenever you have your code and maybe another copy of your code, same program, or maybe even a different process, but there's part of this code is, this is the critical section, this is the critical region. This part here, there's no problem if we're executing this part simultaneously, no problem. But if we get to this point, we want to make sure only one program is running. Whatever, because they need to have access to a certain thing or a certain device, that if the two of them get there, it's going to crash. So what we do, we have here at the very start, you have before you go into the critical section, you have an if statement. It's very simple. You say if this critical section or this variable of this flag is, say, busy, then wait. That's all you have to do. And you go back here and check it again. So you go back, you loop, keep checking. If it's not busy, if it's free, else just turn it on, make t equals 1, let's make it busy, make it appear like it's busy, and go into your critical section. So if you come in and it's free, you turn it on, and you go into the critical section. So this job comes in, this process comes in here, it has to execute the same code. It says if t equals free, or is it busy? And says yes, it is busy. Well then wait for a little while, and go back and check again. Is it busy? Yes. Is it busy? Yes. Is it busy? Yes. So it stays stuck in that line, just repeatedly checking. And then, while this one is executing the critical section, it's absolutely happy and delighted that knows that no one will come in here again until it finishes. When it finishes, all it has to do is say, make this flag, tell them that it's free. Turn 0. So it just goes here and turns this 0. So now indicating it's free. Now the other process comes in here. The next loop, it comes out here and checks, is it free? Yes, it is. Great. Turn it, make it busy. Turn t equals 1. Turn it, and go in. So now it goes in. And as it finishes here, all it has to do is just say, turn t into a 0. Now it's free again for another process. There could be many other processes doing the same thing. And there could be this critical section here and also repeated again in this program. You might. So that's so simple, so efficient, so very little code. Maybe 2 lines of code here, 1 instruction here, 1 line of code after the critical section, and you suddenly, after protecting your system completely, using 3 lines of code and using very little variable, very small variable, 1 integer, or even maybe 1 bit, and you're after protecting this critical section. So it's very simple, very efficient, very easy way of doing it, and you achieve, hopefully, the protection of the... But remember, if 2 processes go in at the same time here, these processes may crash, may stop working, or may cause you problems that cannot be sorted. Okay? Anybody can see any problem with this system? Exactly, yeah. So it's the same problem we had with the trains before, even though it worked, but here we could have the same problem. If the 2 processes get to this point, this very question at the same time, and if the critical section is free, so they both check at the same time. They say, what value is that? And they get the value 0. It's free. Oh, great. Turn it into 1. So this one writes 1 here, thinking it has just booked the critical section. This one says, turn it into 1. So write 1 here. So they both write 1 to the same variable, and they both think that's clear, and they both go into the critical section, they both crash. They have a problem. So that's one problem with this system. And we're going to sort it out, and they did sort it out through some hardware, and they sorted it out using an atomic operation. The atomic instruction, or the atomic operation, they said, when you check for this one here to see is it free or is it busy, and if it's free, 0, change its value to 1. This happens in one atomic operation. You don't wait between them. You don't get interrupted. The operating system, the system will not interrupt you between. If you say, I want those 2 instructions to be executed one after the other without any interruption. So you check, and if that value is 0, turn it to 1 immediately. And it comes back to you and says, yes, it was 0 and it's been turned to 1. So if 2 of them arrive, we cannot allow the 2 of them. Only one of them can check this, and if it's 0, turn it to 1. So when the other one checks, it cannot find it's a 0. It will find that it's 1. So most, obviously, machines now, they have that capability, and it's an atomic operation, and it's sorted out that problem for once and for all. So now, no 2 machines, those 2 instructions will never be able to get the same value. They say, check it. If it's 0, turn it to 1. If it's 1, leave it. Come back and say, sorry, I have to wait. Come back and check it again. Go sleep for a little while and come back and check it again. So let's say this process got in there first. It will turn this into 1, right? And it'll go into the critical section. This one is checking. Is this free? No, it's not. It will wait for a short period of time and then go back again and check it. And keep checking. And keep checking. Check it hundreds of times. As long as this one is in the critical section, this one is checking, keep checking, until this one leaves. And when this one leaves, it turns it into a 0. And then the next time this one checks, now it will find it's 0, it will turn it straight into 1, and it will go in there. Can anybody see any other problem with this? Okay, I'll explain it again. See if you can check the problem. This one comes in. It has booked this, and it goes into the critical section. This is the point. This one comes in. Checks the critical section. It's busy. Waits for a little while, and then go and check again. It's busy. Check again. It's busy. Check again. It's busy. It keeps checking. Wasting resource, wasting CPU resource of checking. You keep checking there, checking. They call this the busy wait. It's like you're waiting for somebody to drive them somewhere, and you're running the car engine. The engine is running, you go nowhere, but you're wasting petrol, you're wasting fuel. So that's called the busy wait. Like you're waiting, you're doing nothing, but you're consuming resources. That's the CPU resource that you keep checking with. So that's called the busy wait problem. So they decided to solve that problem. So this is one of the problems that this test and set system suffers from, or mechanism. So I'll talk about the other issue they have. So now they introduced another system. It's called the test and signal. No, sorry, it's called wait and signal, I beg your pardon. It's the wait and signal. So the next introduction is known as the wait and signal. The wait and signal, they said, let's get rid of this busy wait. How do we get rid of this busy wait? If a process comes in here to check if the flag is 1 or 0, and if it's busy, like it's 1, we keep checking until it becomes free, and say, don't check. You go to sleep. You go wait. You don't consume any resources. You get knocked out. You're finished. You go to sleep. How do you then check when this becomes free? Then we say, it's not your problem. When that becomes free, we'll let you know. Who lets us know? It's the other process that's already in the critical section. When it comes out of the critical section, instead of saying, now the critical section is free, no. First, see if there's somebody waiting and tell them, wake up. If there's anybody waiting, check first. If anybody is waiting, well then wake them up. Remember, this guy is waiting at this point, at this line. If we wake it up, it'll go to the next line. It's no longer a loop. There's no loop. There's only one line. It says, if you're busy, wait. There's no loop back. You just go sleep there. And we'll energize you. We'll wake you up. It's like you go to sleep and your alarm is beside you. So this guy, as they're leaving the critical section, you're there, they press the button and the alarm will wake you up. And they go executing their own code after that. But at least they got you going. And the moment you go, obviously you don't need to turn it on. It's already 1 there, and they go into the critical section. And as your process comes out as well, you check, is anybody waiting? If there is, wake them up. So you have to execute basically the same instruction. Any other process waiting? And if no, well then you have to turn this 0. So you don't turn this into free. You don't say this critical section free unless if there's nobody waiting. So that prevents this busy wait. So now in the new section, the new mechanism, the wait and signal, similar to the test and wait, but at the end when you come out, it's your responsibility to come out from a critical section to see if anyone is waiting to enter the critical section. That's one problem, the busy wait. The other problem is, let's imagine again, this process came in first to check and checked if the critical section is free, and let's say it's 0, it's free. So it says turn it into 1 and go in. So this one is busy using the critical section. This process comes in, finds that the critical section is busy. So it goes into a wait, and it used to go into a loop. Keep check again, and hopefully when this process finishes, it will turn the critical section to 0. Now this one will discover it. Imagine another process just came in. This has been waiting for a few seconds. This process just arrived, and this one has just left, just finished. This guy, before the updating, it's just finished and says, I'm finished. Here's the critical section is now free. This one just arrived. This one, remember, used to go sleep for a little while and then go and check again. Go wait for a little while and then check again. It's just after checking when this one finished. This one finished, turned the value to 0. Of course, the next time it checks, it'll find it. But it just happened that another process just arrived and had a look at the value there and found it's free, and it will turn it to 1, and it will go into its own busy wait, critical region. Immediately after that, this one will wake up again and go check and find, oh, it's still busy, even though not busy, but the same process. Another process has taken over, but this one has just missed its turn. And if it keeps missing its turn, if there are maybe 4 or 5 processes now waiting, this one could keep missing its turn. What do we call that if a process keeps missing its turn? We call it starvation. A process may be starved from getting, from getting the critical region and executing it. So the test and set, the older technique, that technique, or that mechanism, has two problems at least. It has the busy wait problem, where a process comes in and keeps checking in a loop, keeps checking, and by actually checking, you're actually using CPU resources, doing nothing. So we've eliminated that in the wait and signal. Also, you could end up losing your turn, and therefore, if you're unlucky, you could end up being starved for a long, long time. So how do we get rid of that starvation? In the wait and signal, they say when you wait, you don't just wait randomly. Let's have a queue. A queue is so simple, so small, so efficient, easy to do, and it's been around for 50 years in computing, used a lot. So go into a queue. So here's job number 3. Let's say job number 1 is working. Job number 2 comes in. Go to the queue. Don't sit there. Job number 3, 4, could they come in? So they're all waiting in a queue. So when this job that's used in the critical section comes out in the new system, in the wait and signal system, it says, is there anybody waiting? How does it know? All it needs to do is look at the queue. So here's the queue. The queue size, it can check the queue size equals 3 here. There are 3 processes waiting in the queue. So let's say, is there anybody waiting? Yes, just by looking at the queue size we know. So in that case, don't turn this into free. No, wake up the front process, the process at the very front. So we tell J2, hey, wake up. So J2 goes out into the... This one keeps on executing the rest of its code, while J2, process number 2, gets into the critical section. When process number 2 finishes executing, it checks, is anybody waiting in the queue? Yes, okay. When it came out, now it turned out. So yes, it'd say there are 2 processes waiting in the queue. So it'll say, hey, job 3, wake up. And now the queue only has 1 left. Remember, we didn't turn this 0 at all. Because if you turn it into a 0, and another process comes in, checks it, finds a 0, it'll jump in. No, we leave it busy. So even if another process comes in, while just as this one finished, if another process comes in, it will never go in. It will find this busy, it will join the queue. But now, as this process came out, finished, checked and woke number 3, say process 3, get into the, and this goes on, continue executing. Now then process 3 again, waits job number 4, and the queue has a 0. There's nobody waiting now. Now, job number 4, let's say started executing its code, comes in here. Anybody waiting? What's the queue size? That you can ask this question. What's the queue size? Is it 0? Or is it greater than 0? That's if there's somebody waiting or not. If it's greater than 0, then wake them up. Hey, wake, get the front one. If it's 0, if it's 0, what do? There's nobody waiting in the queue. What do we do here? Well, then we go and we say, listen, the critical section is now free. We turn that into a 0. So turn T into a 0. So it's one F statement. If somebody was waiting, wake them up. Else, indicate that this critical region is free. And that's how the wait and signal operate. The wait and signal, as you can see here now, there are 2 functions. Maybe 2 functions of 1 or 2 lines each. One before the critical section and one after the critical section. These were invented by a Dutch guy, so he used the words wait and signal in Dutch. I don't know what they are, but they have the characters P and V. P indicates whatever the word wait. That means check this, and you might have to end up waiting. So we check. If this is busy, we'll wait. If not, we'll turn it into busy, and we go into the critical section. And when you finish, you must issue the V, which is signal the sleepy processes. If they're sleeping processes, we'll signal them. We'll give them a signal to wake up. If not, we just turn the region, our flag to free and leave it and continue. So that solves the two problems. It solves the busy wait and the starvation. How does it solve the busy wait? How did we stop the busy wait in the wait and signal? Instead of a process keeps checking, but how did we stop that?
As soon as it sees that the critical section has been released, it just goes to sleep.
Yeah, and then how does it get awakened when the critical section is free? Yeah, so instead of this one keeps checking the critical section, we give the responsibility to the process that's already in the critical section. As it comes out, wake me up. That's basically what it is, so I don't need to keep waking. Right, how did we solve the other problem of the starvation? How did we make sure a process does not miss its turn? By using a queue. A very simple basic structure of a queue makes sure if you come in first, join the queue. You will get your turn. No one will go ahead of you again. Unless we decide by choice. You as a programmer, you say this process is more important, has higher priority. But you just talk about basic operations. Every process comes in, join the queue. The queue process go in one end, come out of the other end. So we'll guarantee your turn in getting the critical section, and therefore starvation is eliminated. So this weighted signal has two functions known as the P and the V functions, and they are it's the mechanism that's actually used now. It's perfect mechanism. It has very minimum cost. It works correctly. It eliminates, all the busy wait, all the starvation issues, and it's absolutely suitable for parallel processing. And it's still in use, and with very little code to add in. Now, and it solves all the problems normally of critical section problems. But they still came up with another idea, and it's called the semaphore. Why? Why do we need a semaphore when this one works absolutely perfect and there's no improvement actually? The only point here is that we're not going to be eliminating, any more busy wait. There's no busyness, there's no starvation. The only thing that the wait and signal mechanism has, it works perfect for one user into that critical section. If more than one user goes in, it will not allow more than one user to go in. And that's what it's supposed to do. But they found in some systems that we can actually accommodate 2 users or 4 users. So we want something, it will not work if we say, hey, we need 3 users to go in there. For example, imagine you're implementing a petrol station or simulating a petrol station. You say, right, in this petrol station we have 4 fuel pumps, so we can accommodate 4 cars simultaneously. So we can allow 4 users or processors to go into our critical section, but no more than 4. That cannot be simply done by the wait and signal. So, and hence they introduced this semaphore. So the semaphore is a more general mechanism, more general wait and signal, more generalized way of, it will work for 1, it will work for 2, it will work for 7 users of that critical section. Depends what your critical section is, okay? So, and it's probably the most commonly used now and the most famous, and not at much more expense. It basically operates the same. So you need to be able to explain how does the wait and signal work, but also how does the semaphore work. And they work somehow, similarly. Let's go back and just go over the wait and signal. The wait and signal, it has a variable, right? Every critical section you need to have a variable for it. If you have more than one, have few variables. But for one critical section, you need one variable. And that variable normally will have the value 0 or 1. Normally 0 for free and 1 for busy. And it has those two functions, the P and the V. One must be issued before approaching the critical section. That's the wait. And another one at the end of the critical section, just to signal any waiting processes. Now, the semaphore works in pretty much similar. So it also needs a variable. I'm just going to call it S here, just to indicate the semaphore. You can give it any name. It's a variable name. Now, this one has a 0 or 1 usually. This one, and this starts with a 0. Whenever you start initially, you start with the value 0. The semaphore, it has a value 0, but that's not the starting point. 0 means busy, fully used. It starts with another number, the maximum number that we are allowed in our system. Let's say you're going to implement some process that can allow 3, or a critical region that can have maybe accommodate 3 users, but no more than 3. And that's the number you start with, 3. So some number that's the maximum users allowed. So you start with the numbers. That's one difference between them. Many start explaining maybe semaphores or programming semaphores, and they started with the value 0. Wrong. You started with the maximum allowable. It's just to reduce the problem and the complexity here. There's an example, very simple example. You look at a semaphore, for example, like a hotel that has a number of rooms for rent. And the number here is the number of free rooms, the number of keys you have. So in this case here, we have 3 keys. As you go into the hotel for a reception, you'll have 3 keys. So you go in, a process comes in, let's say a user, and says, I need a room. Oh yeah, there are 3 rooms. There are 3 keys. So what it does, let's say here's the critical section. Well, let's go for the hotel, because it's pretty much the same idea. But once you get that idea, so you go in. If the number is greater than 0, that means we have rooms. So you can use them. So a process comes in. First thing it does, if this is the critical section, or critical region, then before the critical region, you issue this command. Whatever here, you test for the variable. If it's 0, that means if it's free. Here, no. You see, if it's free, that means if it's bigger than 0. So if S is greater than 0, that means, yeah, we can use it. If it is 0, what happens if it is 0? If it equals 0, that means you can't go in. It's busy. What you do, you have to wait. You go to sleep again. Same idea as this one. You get knocked out. You can't come out of it until somebody wakes you up. Now, if there is a key, it's not a 0, there is a key. What do? You take that key, so the number of keys will get reduced. Else, so S equal S minus 1. So you take that key, and now there are 2 rooms left in the hotel. And you go into the critical region. Supposing another user comes in. They want to go into the same critical region. They have to issue the same request. If S equals 0, then wait. They look, it's not, sorry, this one has turned into 2. No, there are 2 keys. Well then, else take one of those keys and go into the critical region. So one of the keys are gone, and now there's 1 room free still. So you're in the critical region. Another process comes in. You issue the same request. If S equals 0, then wait. Else take this key. S equal S minus 1. And there it is, you've taken the other key. Now there are 3 processes inside the critical region, no more. So what do we do? Another process comes in. What happens if this process arrives? If S equals 0, then wait. Yes, it is 0. Sorry, go into the queue and go sleep. So his job number 4 is waiting. That's job 1, job 2, job 3, and job 4 cannot go in, so it's waiting. So it's waiting here. There's an else. It will not, of course, it will not reduce S equal S minus 1. We'll never do it because it went into that F statement. If we wake it up, it'll go straight into the critical region. But it's not. It's still waiting outside. Now what happens here? One of the processes, let's say process number 2 finished first. What does it do? It has to issue similar function to the one here, to the V. So it says, is there anybody waiting? Of course, here when you go into the queue size equals 1. So there's somebody waiting. We say, what about the queue size? First thing you check, is the queue size equal 0? Or is it greater than 0? If so, then wake them up. Go to the critical region and wake this one up. So this one will wake up and go straight into the critical section. This will do nothing, will not leave the key. It's like this guy is leaving the hotel, they have a key. They don't give it to reception. They find somebody is waiting there for the room. Hey, you're waiting for that room, here's the key. They hand the key straight. So if another process comes in, they will not pick the key from reception. The key is never left in reception as long as somebody is waiting here. And therefore, we'll guarantee only 3 will go into those critical sections. So this one has finished. It's not in the critical section anymore. And there are no more rooms free, but this one has gone in and is executing. So let's say this one here is finished as well. So it checks. Now remember, when we took this out of the queue size is 0. There's nobody waiting now on any more keys. What happens next? If the queue size greater than 0, then wake them. If is the queue size? No, it's not greater than 0, it's 0. Well, then don't wake anybody. You don't have to wake anybody. There's nobody to wake. Else, what you do is you give the key back. You say S equal S plus 1. You give the key back to reception. Now there is a key. And you carry on. So this part here is the function that's executed after the critical section. Then you carry on executing your own code afterward. So now there is a key. If another process comes in, there is a key they can take. And that's how the semaphore works. So semaphore, to start with, they start with the maximum number of users allowed into the critical region. You start with 2 or 3 or whatever the maximum number. Every time a process comes in, we decrement that number. That number is decremented until it's 0. If it's 0, that means it's fully utilized. We can't take any more. The other one, the previous wait and signal, it starts with 0. That means it's free. If it gets if somebody comes in, it's incremented to 1. That means the critical region is busy. Okay? Everybody okay with that? And that's how we can synchronize or control parallel processes that are executing in the same memory, the same device, from, getting into critical sections that could cause problems. Using very simple techniques, very simple mechanisms. Semaphore is a fantastic mechanism. Again, it's very efficient, very little code, but needs to be executed before the critical region and after the critical region. You can write it in your own code. You're the programmer. You decide, okay, this part of my code is quite critical. I don't want 2 processes going in there or 3 processes. Then before that, once you identify it, before that you write those 2 lines and those 2 lines after it. It's an F statement basically in each one of them. The process that goes in is responsible to check if there's anybody waiting when it comes out. The processes that wait, they have to wait in a queue so they don't lose their turn again. Okay? All right. This is all we need to talk about today. And tomorrow we'll talk about how to actually implement it in a practical terms of cooperating processes. A number of processes that work together. It became kind of a good technique, maybe instead of writing 3 separate programs, one to take some input, process it a bit, give it to another process, and then another process takes that input. So if you have a process generating something that can be used as input to another process, so this is process 1, process 2, that process this and passes it on to another process as input to another process, and so on. It's just like in a factory. You build something and you pass it and it keeps moving onto the belt and keeps added by different processes or users or workers until you end up with a final product. You could also do that on programming. And in order to do that, they keep passing, for example, messages or products to one another. Usually you put these in a queue, but in queues sometimes, if this one keeps filling into a queue, once the queue is full, we need to be able to synchronize and say, hold on, don't put any more stuff in the queue until this one takes some stuff from the queue. Remember, if you've started programming and you start taking things from a queue, and if there's nothing to take from a queue, but your program says take something from the queue, your program will crash. You need to know when not to start drawing things from a queue if it's an empty queue. Or vice versa, if you're putting something on top of a stack or taking things from a stack. If there's a stack of a few things on top of one another, you keep taking them, and there's nothing left, and you keep saying take more from the stack, your program will crash. So we need to synchronize those, and we'll talk about that tomorrow, I think. Any questions so far? Good. Now, let me ask the question. Tell me, what are the problems with the first oldest mechanism, the test and set? Does it have any issues or problems? The test and set mechanism for synchronizing critical regions.
There is a problem.
Yes? Give me one problem.
Like two processes are simultaneously.
Just give me the name of the problem. What do you call that problem that it cannot sort? The busy wait. What is the busy wait? Anybody can tell me what the busy wait is? What do we mean by busy wait?
When two processors are accessing the same thing.
No? What's a busy wait?
When a process is waiting, it is constantly checking and wasting CPU time.
Yeah. Okay. So if a process is waiting for something, for some resource, and if it keeps checking for the availability of that resource, that's actually consuming resources, consuming CPU time checking. And if it keeps checking, that's a lot of wasted CPU time. Right. So how did we sort out the busy wait situation? That's in the test, yeah, in the wait and signal.
When the process sees that it's busy, then it go to sleep and wait for the process using in the process session to finish it in a wait.
To signal it, to allow it, yeah, to let it know that the resource is available. So we no longer, it's not a good practice, even if you have to do it. Never have a loop that going around checking something, you know. But to stop that process, and when that thing you're checking for becomes available, then let that process signal the waiting process. Okay. What's the other problem? That's busy wait and starvation. Right. What do we mean by starvation here?
If we already had one process running, another one waiting and checking, and another third one comes, and exactly in the moment that the first one releases
the resource,
and exactly in the moment that the other one is waiting, so you can get the turn of the second one.
Okay. So basically,
Like this.
if a process misses its chance or its turn, then if it keeps doing that, then it's starved. It can be starved from the resource. So a process may be starved from a resource if it keeps missing its opportunity to use that resource or its turn. And how did we eliminate that problem? By going waiting in a queue. So at least in a queue, it's very easy. We know who's been there first. First in, first out, generally, in queues. So the queues are known for first in, first out. Stacks are known for first in, last out, or last in, first out, sorry. Yeah? Okay. And what's the advantages of a semaphore? Yo, stay with me here for a sec. Give me one advantage of semaphore over test and set. Semaphore. How good is it?
It's good. It allows
it allows multiple users in the same critical section, any number of users that we choose. Any other advantages? What advantages does the semaphore have over the set and wait? What advantages does semaphore have over the set and wait? Not the wait and signal, over the oldest techniques, set and wait. Test and set, sorry, did I say? What's test and wait? Yeah, test and set. Okay, I was just testing you. Right, okay. Any advantages? What's the advantage of semaphore over test and set? It eliminates, doesn't have the busy wait, and it doesn't have the starvation problem, and it allows any number of users. So semaphores are, you know, they have basically all the advantages. So if we use a semaphore, see, a semaphore can allow 2 users, 3, 4, 1 user if we want. If it allows only 1 user only, that means its variable, it starts with 1. And if that somebody's in the critical region, it goes into 0. That means no one else can go in. And then as that user leaves, it goes into 1. So it keeps switching between 0 and 1, just like the wait and signal, 0 and 1. So if it keeps just switching between 0 and 1, that only allows 1 user. We call that, so they start giving it another name. They call it the binary semaphore. That's a 0 and 1 semaphore. So they have multiple names for semaphores. They also call it mutex. Mutex, that's mutual, short for mutual exclusion or mutual exclusive mechanism. So it allows mutual exclusion to a critical region. But it's also known as the binary semaphore. So the binary semaphore is a semaphore that can only have 2 values, 0 or 1. That means it's only protecting a critical region that can only be used by 1 user only. But remember, with semaphores, we can allow to use maybe a critical region that can be used by 2 or 3 semaphores or users simultaneously. Okay, so we'll go through the slides, hopefully. Any questions? No, it's the same. It's a semaphore. It's just general. It can be used for 1 user, allows 1 user, or 2 or 3. It's the advantage is that maybe in your code, if you decide, no, I'm going to go for 2 users instead of 1, just change 1 variable and that's it. You know, not even change the variable, change the initial value. You know, it's easier to code or modify your code rather than. But the wait and signal works just as well for 1 user. Right, okay. The concurrent processing, hopefully, between today and tomorrow. You should be able to know the difference between processes and processors and their connections. Oh, you already know that. Differences among common configuration of multiprocessing. So we look at the different configuration of CPUs and processors within a system from a hardware point of view, but the significance of critical region in process synchronization, so how important these critical regions are, and the basic concepts of process synchronization, how do the actual mechanisms that are used to synchronize processes to And what we mean by synchronization is it slow one, wait, tell one to wait, and another one to continue, when to stop and when to continue, in order to avoid, problems. So we looked at the three mechanisms: the test and set, wait and signal, and the semaphore. So again, the need for process cooperation, something we'll be talking about tomorrow, in several processes working together, and how a number of processors executing a single job, they can cooperate. So we look at similarities and differences between processes and threads. We've already talked about threads, and the significance of concurrent programming languages. So these are some of the languages that allow concurrent programming. Right, we've just mentioned in the past the kernel, so we've already talked about it in a previous lecture, so I'm going to skip this now. Back to parallel processing. What do we mean by parallel processing? Two or more processors operate together, which means two or more CPUs executing instructions simultaneously. So when we get into parallel processing, we generally are talking about more than one CPU, multiple CPUs executing together simultaneously. They're either executing different programs or parts of the same program or even parts of the same instruction. A processor manager needs to coordinate the activity of each processor. So we need a processor manager. And if there are more than one CPU, then the processor manager needs to basically manage and schedule each of those processors. A processor manager needs to synchronize the interaction among these CPUs. So CPUs might need to exchange information or access the same information or access same memory or devices, files, open or close files. The reasons for development of parallel processing, obviously it's obvious: enhanced throughput. We want to improve our throughput. So if we had 6 CPUs, we'd be able to execute a lot more code than if we had only one CPU in the same device. And also to increase the computing power. So the more CPUs, obviously the better. The benefits of parallel processing: reliability can be increased, even though obviously it increases complexity. It's a lot more complex and more difficult to have programs or have machines with multiple CPUs. But at least once we get them going, if one of the CPUs decides to stop, breaks down, at least the rest of them will continue operating. So that's extra reliability. It's faster processing. It's obvious if you have more CPUs, then we can execute as many instructions as all the CPUs together. How do we do actual parallel processing? Either each CPU is given a separate program, separate job to work on it, which is just like you have your own single CPU and you allocate it one program. So while we have another CPU beside it, it will have a separate program. Or CPUs are allocated to each working set or parts of a program. So a job or a program may be split into maybe 4 parts, and every part is given to a different CPU. If you had 4 CPUs, it will execute faster. Individual instructions is the next level. Instead of splitting a program into different parts, now you can take one line of code, one instruction, and split it into different parts, especially mathematical operations, where you say divide this by this and subtract this and multiply them by this. So you can send different parts of the instruction to different processors and get the result together. So 2 major problems here: how to connect the processors into some configuration, that's a hardware kind of a problem, and how to actually interact or cooperate or synchronize those CPUs working together or those processors working together. So just a brief look of how actually they're connected together. And there are kind of generally three methods where the CPUs are connected together. They either have one master CPU and a few slave CPUs where it controls them, kind of using the master-slave model, or they're connected together, they're equal, they're the same, but they're loosely connected. They're not very strongly integrated, or symmetric, where kind of everything is pretty much the same with each of the CPU. So the master-slave one first, just it's easier to look at the diagram. The master-slave one, where the number of CPUs here in this example here, there are 3. The center one is the main one. And it's the one that does all the scheduling, or it's all the one that decides what program goes where. And it's the one that's in control of all the input-output devices, so everything has to go through the main CPU. But it's easier to control. It's easier to control all the other CPUs. So this one might get a program, might decide to split it into 3 parts, give one part to that one to execute. If that one needs to print something, it has to go through this master CPU to send it to the printer. So this one kind of controls basically everything, and they all have access to the same memory, so they can share memory, but they cannot share they can share their I/O devices, but only through the master process, which is good. You can also control. You kind of feel in full control of the operations that are happening. But of course, if that master processor stops working, the entire system stops. So there's a kind of a single point of failure here. Reliability depends on how well that processor works. Also, because all your input-output operations, see the CPU can control those or cooperate with them or issues commands to them directly. But as you notice here, each time that CPU is executed, it needs to an I/O operation, it has to go through the master slave. So there's a lot of I/O interrupts happening to the master CPU, instead of each one handles its own I/Os. So I'll just go back to the bit of write-up about the master-slave arrangement. It's an asymmetric multiprocessing system. Asymmetric, that means they're not the same, the CPU, the master, and the slave one. A single processor system with additional slave processors, and each of which is managed by the primary master processor. So there is the primary main one that looks after the entire system. The master processor is responsible for managing everything, maintaining the status of processes in the system. So it looks after all the processes in the system, performing storage management, looks after the storage that's in main memory, and it also looks after the devices, schedule the work for the other processes, and executing all control programs. So it's doing most of the work. It's a simple way to do it, but reliability is like if it breaks down, the master one breaks down, then the entire system stops, and can lead to poor use of resources, because the same resources are controlled by the same CPU, and the number of interrupts is huge because they all have to go through one single processor. The next system is a loosely coupled configuration. So this is something like, it's like you have a laptop, you have another laptop sitting on top of it, and another laptop. They're almost independent of one another. Each, like you have 3 CPUs or more, as many CPUs. Of course, they're all built into the same system, but they all have their own, each one of them has its own main memory, and each one of them has its own I/Os. So it's relatively easy to use and to implement, but maybe efficiency is not great. Each processor has a copy of the operating system and controls its own resources and its own memory, and each can communicate and cooperate with the others. But once a job is allocated to a process, that's it. It's stuck with that processor. You cannot move it around. And each has a global table that indicates to which processor each job has been allocated. So as jobs come in, the operating system will say, right, you go to processor number 1, and you stay with processor number 1. Job scheduling is based on several requirements and policies, and if a single processor fails, the others can carry on. So it has better reliability than the previous one. And it's not just complex, but efficiency is not great. The next one is the symmetric configuration, where the processor scheduling is decentralized and each processor are of the same level and same type. And it's more reliable, it uses the resources more effectively. So basically, the other time, I don't have a diagram for the, there it is. So you have 3 separate or many processors, and they all share the same I/O devices, they all share memory, they have access to the same memory. And it seems to be much better, more efficient, and more reliable as well. And if one of the CPUs stops, one of the processors, the others will carry on. And there's easier transfer of processes from one processor to another. And also there's better cooperation than previous systems. So all processes must be well synchronized to avoid various problems, because now they're sharing same resources and sharing memory. The symmetric one, it uses resources more effectively, it can balance loads well, and can degrade gracefully in the event of failure. It doesn't just collapse, it tries to terminate jobs nicely. But because they share same memory, same resources, you're bound to have deadlocks, you're bound to have starvation if you don't perform, if you don't do proper synchronization. Any given job or task may be executed by several different processors. So you can take a program or a job, split it into different parts, and each part goes to a different processor, and they will work together. They're more complex as several processors try to access the same resources. And these conflicts can be cleared or reduced or prevented by proper synchronization. So process synchronization is necessary here, and there are the algorithms to resolve conflicts between processors while using resources such as memory maybe or other resources. So process synchronization software, that's what we have been talking about, is for successful process synchronization you need to use resources, or resources must be locked. Normally, the normal operation is lock a resource while you're using it if you don't want anyone else to use it. But a waiting process is allowed to use the resource only when the resource is released or becomes free. But if there is a mistake here, we could end up having job waiting indefinitely, or maybe we could end up having deadlocks. So if you don't manage it correctly, you could either have starvation or deadlocks. And hence, those mechanisms that we are talking about. A definition of what a critical section is. Critical section is a part of a program that must complete execution before other processes can have access to the resource being used. So if a process is executing this part of a program or a process, no other process should execute the same part. That's the critical region. It's such a critical, such a sensitive part of your program that if the instructions in those copies, 2 copies, are executed at the same time, you could end up having a problem. So processes within a critical region cannot be interleaved without threatening the integrity of the operation. Okay, so if you run 2 or more processes in a critical region, you can just think of it as another resource that's absolutely critical, that's mutually exclusive. Just like on hardware, on, say, a printer. You want to send 2 printing jobs to the printer simultaneously. If you do it without any protection, you're not going to have good results. It doesn't work because the printer is not a shareable device. Similarly here with a critical region, but that's part of your code, that before you go near a hardware or anything, you're going to have a problem if you're on that part of code. It could be updating variables, it could be updating files or records in a file, it could be anything, it could be dealing with queues and stacks on memory, but you know that part is critical and should not be executed by more than one. That we call that the critical region. So synchronization is sometimes implemented as a lock and key arrangement. As a process must first see if the key is available, and if it's available, then the process must pick it up and put it in the lock to make it unavailable to allow other processes. So those three mechanisms that are used on the basis of lock and key are the test and set, wait and signal, and the semaphores. So the test and set, we already talked about it. It's an indivisible machine instruction. So it's an atomic machine instruction. So there are two instructions that must be done simultaneously, cannot be interrupted. Checking a variable and changing its value. If it's 0, you say check. If it's 0, turn it into 1. Those two operations must happen simultaneously, cannot be interrupted. We call them an atomic instructions, or an indivisible instructions executed in a single machine cycle to see if the key is available, and if it is, then set it to be unavailable. And when we talk about key, we check, is that value 0? If it is, turn it into 1. That means, can I, go into that section? If I can, great. Then turn it 1 so no one else can go. And the actual key is a single bit in a storage location that can contain either 0 or 1. 0 for free and 1 for busy. And remember, it's important to remember, the 0 is free. In the semaphores, it's the other way around. 0, that means it's busy. But here in the test and set, 0 is free. A process P1 tests the condition using a TS instruction. That's test and set instruction, before entering the critical region. So you must do the test before you go into the critical region. When you finish the critical region, you must turn it back into available. So basically you check it. If it's free, make sure it says I'm not free anymore. And when you leave, just as you leave a room, a meeting room, before you go to the meeting room, you indicate on the door it's busy now. Don't want any interruptions. And when you finish the meeting, you come out and you make it a sign on the door that says it's free. So if no other process is in the region, then the process 1 is allowed to proceed, and the condition code is changed to 1. So you check if it's free, then you're allowed to proceed, and you turn it to 1. That means it's busy, no one else to come in. And when process 1 exits, when you leave, you turn it back to being free again. So the advantage of that is very, very simple, and it works well for a small number of processes, but it doesn't always work well. Starvation could occur, so it has that problem of starvation. Starvation, that means if while you're in the critical section, you're using it, another process comes in to use it, finds it busy, they go and wait. And they keep checking. Another process comes in, maybe if I'm just finished, the second process could go in first. So that's leaving the first process, the other process, to be starved of the resource. Process gain access in arbitrary fashion. That's the reason why, because it's randomly. You don't know when you're getting your turn. It depends on how often you check. And if you keep checking continuously, you're wasting a lot of resources. If you keep checking every few moments of time, that's the moment of time that you might miss it when it becomes available. So the waiting process remains in unproductive, resource-consuming waiting loop. It's called the busy wait. So the busy wait is an unproductive, resource-consuming wait. So you're a wait, but you're waiting for some resource, but you're actually using the CPU. So the next mechanism we talked about is the wait and signal, which is basically a modification of the test and wait signal. And it introduced a queue to prevent this starvation. And it actually introduced the responsibility of coming out of the queue of the wait on the process that's actually using the resource or the critical section. So if a process comes in, is responsible to wake the waiting process up. So these are the two major differences. So it's the two new mutually exclusive operations. So now they have two operations. One is the wait, and one is the signal. The wait is activated when the process encounters a busy condition. So you check your resource. If it's busy, then you go into a wait signal, a wait condition. And when you finish the critical region, you issue the signal to see if there's any waiting processes to let them go. And that works for one single user for a critical region. The next process is called the semaphore, the next mechanism. So the mechanism is similar to the wait and signal, except the wait and signal only works for one user for that critical region. Now with the semaphore, we are free to utilize any part. So the semaphore is a non-negative integer. Remember, with the number, with this semaphore number, we said increment and decrement, but it always starts with 0 and goes up. Or sorry, it starts with a maximum number, it goes down as far as 0 and goes up again. It never goes into a negative number. With this one here, it flips between 0 and 1. But with the semaphore, we start, say, with 3, it goes down to 0 and up to 1, 2, 3, 0. It keeps moving between that. So it never goes into a negative value. The two operations to operate on the semaphore are the P and the V. That's one is called test, and the other one is the signal and increment. The semaphore work basically by allowing or not allowing the critical region to be available or not available. These are the old signals that were used in trains. And this is basically the code for the V, that's the part that's issued after the critical region. It checks first if there's anybody waiting. If nobody's waiting, then we'll increment. That's we leave the key. So now we have an extra key in the hotel. Think of the hotel with the semaphore. If you forget, does it add or does it decrement? And the one before going into the critical section, for a semaphore, if you end up taking one of the keys, that means the number of keys is reduced by 1. So it ends up decrementing. Only if it's free. If the S is greater than 0, that means if we have keys, still we can go into the critical region, then the number will be greater than 0. And if it is, you can decrement it and go in. So 0 implies that the busy critical region, it's fully used critical region, and the process is calling. If you find it says 0, the variable here is 0 on semaphore, then you must wait. Guys, I can't hear myself there. All right, we go through this section, then we take a break. This slide here. Now, I don't have my indicator with me. But right, so this is an example of a semaphore. A number of processes arriving. So the first process arrives at the first time with semaphore. This semaphore is a binary semaphore. It starts with the value 1. That means it's controlling a critical section that can only be used by one user only. So that's why we initialize its value at 1. Now, at this moment of time, process number 1 arrives and issues the P function, saying, hey, I'm checking I want to go into the critical section. Is it available? And so it checks the value, and it finds that the value is 1. If it's not 0, that means we can go in. So it goes in and decrements the value from 1 to 0. At the next moment of time, process number 1 finishes, comes out of the critical region. Remember, see the semaphore turned into a 0. That means any more processes coming in, they cannot come in. No more. So process number 1 moment of time number 2 finishes, it issues the function VS. That means I'm finished with the critical section. Anybody waiting? No, there's nobody waiting. Well, in that case, turn the 1 or the 0, that was 0, turn it into 1, and indicating that now the critical region is free. It's available to be used by one more user. So at moment of time number 3, process number 2 arrives. It issues the P request. It wants to check, it wants to go into the critical section. It checks the variable. It's 1. That means I can go in. It decrements it to 0 and goes in. So now process number 2 is in critical section. After that process, while process number 2 is in critical section, process number 3 arrives. It issues the request, PS. Can I go into the critical section? It checks, no, it's 0. That means he cannot go in. No more keys are available, if this was a hotel. So then it waits. As process number 3 is sitting, waiting, it's blocked. And it cannot move until it's signaled by someone else. So the critical region variable S is still 0. Now another process arrives, process number 4. It issues the request, can I go in? No. The critical region says 0, you can't go in, you join the queue. So now we have 2 processes waiting. At the next point of time, process number 2 finishes. So it issues the V. The V says, is anybody waiting? Yes, there are 2 processes waiting, P3 and 4. We'll then release signal P3. P3 goes into the critical region, and process number 2 disappears, executes other things. The next moment of time, there is no event, nothing happening. Nobody's leaving, nobody's coming. Process number 3 is still in the critical region. Process number 4 is still blocked. Semaphore still has the value 0. At the next moment of time, process number 3 finishes. It issues the VS. Is anybody waiting? Yes, process number 4 is waiting. Signal it to go into the critical section, and process number 3 leaves. Does it increment the variable? No, it doesn't. So it's like you have a key, you hand it to the next process. You don't increment it or... Finally, process number 4 leaves, issues the VS. Is there any process waiting? No. Well, in that case, we increment the variable, say, here's a key, and that's gone to 1. Is this clear? This is, yeah, it's a semaphore, but because it only allows one user, it only flips between 0 and 1, it's known as mutex or binary semaphore. What time do we finish? Oh, I'm sorry. I thought it was 6 and I was taking my time. Okay. Has everybody signed the attendance sheet? Sorry, I'm sorry.